Effective Kotlin. Item 2. Eliminate critical sections. When multiple threads modify a shared state, it can lead to unexpected results. This problem was already discussed in the previous item, but now I want to explain it in more detail and show how to deal with it in Kotlin JVM. The problem with threads and shared state. While I'm writing these words, many things are happening concurrently on my computer. Music is playing, IntelliJ displays the text of this chapter, Slack is displaying messages, and my browser is downloading data. All this is possible because operating systems introduced the concept of threads. The operating system schedules the execution of threads, each of which is a separate flow. Even if I had a single core CPU, the operating system would still be able to run multiple threads concurrently by running one thread for a short period of time, then switching to another thread, and so on. This is called time slicing. What is more, in modern computers we have multiple cores, so operating systems can actually run many operations on different threads at the same time. The biggest problem with this process is that we cannot be sure when the operating system will switch from executing one thread to executing another. Consider the following example. We start 1,000 threads, each of which increments a mutable variable. The problem is that incrementing a value has multiple steps: getting the current value, creating the new incremented value, and assigning it to the variable. If the operating system switches threads between these steps, we might lose some increments. This is why such code is very unlikely to print 1,000. I just tested it, and it printed 981. To better understand this problem, just consider the following situation that might occur if we had started two threads. One thread gets value 0, then the CPU switches execution to the other thread, which gets the same value, increments it, and sets the variable to 1. The operating system switches to the previous thread, which then sets the variable to 1 again. In this case, we've lost one incrementation. Losing some operations can be a serious problem in real-life applications, but this problem can have much more serious consequences. When we don't know the order in which operations will be executed, we risk our objects having incorrect states. This often leads to bugs that are hard to reproduce and fix, as is well visualized by adding an element to a list while another thread iterates over its elements. The default collections do not support their elements being modified when they are iterated over, so we get a concurrent modification exception. We encounter the same problem when we start multiple coroutines on a dispatcher that uses multiple threads. To deal with this problem when using coroutines, we can use the same techniques as for threads. However, coroutines also have dedicated tools, as I described in detail in the book Kotlin Coroutines Deep Dive. As I explained in the previous chapter, we don't encounter all these problems if we don't use mutability. However, in real-life applications we often cannot avoid mutability, so we need to learn how to deal with shared state, by which I mean a state used by multiple threads. Whenever you have a shared state that might be modified by multiple threads, you need to ensure that all the operations on this state are executed correctly. Each platform offers different tools for this, so let's learn about the most important tools for Kotlin JVM. Synchronization in Kotlin JVM. The most important tool for dealing with shared state on the Kotlin JVM platform is synchronization. This is a mechanism that allows us to ensure that only one thread can execute a given block of code at the same time. It is based on the synchronized function, which requires a lock object and a lambda expression with the code that should be synchronized. This mechanism guarantees that only one thread can enter a synchronization block with the same lock at the same time. If a thread reaches a synchronization block, but a different thread is already executing a synchronization block with the same lock, this thread will wait until the other thread finishes its execution. The following example shows how to use synchronization to ensure that the num variable is incremented correctly. In real-life cases, we often wrap all the functions in a class that need to be synchronized with a synchronization block. The example below shows how to synchronize all the operations in the counter class. In some classes, we have multiple locks for different parts of a state, but this is much harder to implement correctly, so it's much less common. When we use Kotlin coroutines, instead of using synchronized, we rather use a dispatcher limited to a single thread, or a mutex, as I described in the book Kotlin Coroutines Deep Dive. Remember that thread switching is not free, and in some classes it is more efficient to use a single thread instead of using multiple threads and synchronizing their execution. Atomic objects. We started our discussion with the problem of incrementing a variable, which can produce incorrect results because regular integer incrementation has multiple steps, but the operating system can switch between threads in the middle of these. Some operations, such as a simple value assignment, are only a single processor step, so they are always executed correctly. But only very simple operations are atomic by nature. However, Java provides a set of atomic classes that represent popular Java classes, but with atomic operations. You can find atomic integer, atomic long, atomic boolean, atomic reference, and many more. Each of these offers methods that are guaranteed to be executed atomically. For example, atomic integer offers an increment and get method that increments a value and returns the new value. The example below shows how to use atomic integer to increment a variable correctly. Atomic objects are fast and can help us with simple cases where a state is a simple value or a couple of independent values. But these are not enough for more complex cases. For example, we cannot use atomic objects to synchronize multiple operations on multiple objects. For that, we need to use a synchronization block. Concurrent collections. Java also provides some collections that have support for concurrency. The most important one is concurrent, which is a thread-safe version of HashMap. We can safely use all its operations without worrying about conflicts. When we iterate over it, we get a snapshot of the state at the moment of iteration. Therefore, we'll never get a concurrent modification exception. But this doesn't mean that we'll get the most recent state. When we need a concurrent set, a popular choice is to use new key set from concurrent, which is a wrapper over HashMap that uses unit as a value. It implements the mutable set interface, so we can use it like a regular set. Instead of lists, I typically use concurrent linked queue when I need a concurrent collection that allows duplicates. These are the essential tools that we can use on the JVM to deal with the problem of mutable states. Of course, there are also libraries that offer other tools that support code synchronization. There are even Kotlin multi-platform libraries, such as Atomic FU, which provides multi-platform atomic objects. Let's change our perspective back to the more general problem with mutable states and explain how to deal with it in typical situations. Do not leak mutation points. Exposing a mutable object that is used to represent a public state is an especially dangerous situation. Exposing a mutable object that is used to represent a public state, like in the following examples, is an especially dangerous situation. Take a look at this example. One could use load_all to modify the private state. This situation is especially dangerous when such modifications are accidental. The first thing we should do is upcast the mutable objects to read-only types. In this case, it means upcasting from mu_task_dk to list. But beware, because that change alone is not enough to make this class safe. First, we receive what looks like a read-only list, but it is actually a reference to a mutable list, so its values might change. This might cause developers to make serious mistakes. Second, consider a situation in which one thread reads the list returned using load_all, but another thread modifies it at the same time. It is illegal to modify a mutable collection that another thread is iterating over. Such an operation leads to an unexpected exception, a concurrent modification exception. There are two ways of dealing with this. The first is to return a copy of an object instead of a real reference. We call this technique defensive copying. Note that when we copy, we might have a conflict if another thread is adding a new element to the list while we are copying it. So if we want to support multi-threaded access to our object, this operation needs to be synchronized. Collections can be copied with transformation functions like toList, while data classes can be copied with the copy method. A simpler option is to use a read-only list, as this is easier to secure and gives us more ways of tracking changes in objects. When we use this option, and we want to introduce proper support for multi-threaded access, we only need to synchronize the operations that modify our list. This makes adding elements slower, but accessing the list is faster. This is a good trade-off when we have more reads than writes. Summary. Multiple threads modifying the same state can lead to conflicts, thus causing lost data, exceptions, and other unexpected behavior. We can use synchronization to protect a state from concurrent modifications. The most popular tool in Kotlin JVM is a synchronized block with a lock. To deal with concurrent modifications, Java also provides classes to represent atomic values and concurrent collections. There are also libraries that provide multi-platform atomic objects, such as atomic FU. And finally, classes should protect their internal state and not expose it to the outside world. We can operate on read-only objects or use defensive copying to protect a state from concurrent modifications. This was an item from the book Effective Kotlin, which covers best practices and philosophy of good quality programming in Kotlin. It covers all important aspects of programming, such as safety, readability, reusability, performance, abstraction, and class design. You can find it on LeanPub or Amazon. Its author, Marcin Muscala, offers consultations, workshops, and courses. All links in the description below. I hope you enjoyed it. Cheers!